Okay, this video will give you a short introduction on how to use R to write your own program to simulate a probability experiment. The particular experiment that we're going to consider is the two-die roll, I should say the sum of the two-die roll, and its outcomes. So let's go ahead and get started. The first thing that we'll need to do is get a working copy of R running. If you've downloaded R, you should be able to find a copy of R in your program files. I'll go ahead and open up the 64-bit version, and you should, when initially opening R, see an environment similar to this. So R comes prepackaged with a number of drop-down files, which are fairly self-explanatory, but I'll let you explore those as we go. And then the one workspace that's opened up automatically always is the R console, and then there is a blank workspace that surrounds it. The R console is a place where you can run single lines or multiple lines of program code. So for example, you can use it a lot like a calculator. You can do things like 3 plus 4, enter, and it'll give an output of 7, or you could do something like let's let s equal to 5 and t equal to 4. It'll store those two numerical values to those two object names, s and t, and then you can operate on them, such as s times t or s raised to the t, to obtain arithmetic results. You can run whole programs over here by writing multi-line codes and hitting enter, but the problem is that once you run them, you are not allowed to go back up and edit. So I can't edit, for example, these previously run lines in the console, which makes it fairly hard to work in the console to develop or craft something over the course of time. You're also not allowed to save in the R console. It's strictly an environment where things are run. So in order to write programs, you need a second window to open. And that's done by going to File, New Script. And a script is what we would think of as a program writing environment, a place where we can write multi-line sets of commands and then run them in the console. It's my preference usually to tile these windows vertically, so I'll go ahead and tile them vertically. So you can see that we have two environments now to work in, the R console on the left and the R editor on the right. It's in the editor where we will write the program, and it's in the console where we'll run and evaluate the contents of the program. Okay, the other thing that you should be aware of is that the R editor, when it is highlighted when you're working in that particular environment, you can save. So I'll go ahead and save my script to the desktop as die roll, because we are going to investigate the two-die sum. Okay, so let's go ahead and get started with the construction of the program that's going to simulate the die roll sum. The first thing we should probably do is start simple, not attack the whole problem at once, but let's go ahead and see if we can get R to roll a single die for us. One way we could accomplish that task is by creating an object, which we'll call die, and storing to that object using a left-hand arrow, which is a combination of a less than symbol and a dash, a vector of values. So the vector of values will be the values 1 through 6, and this will be our die. Now anytime you input a vector in R, you want to call it out with a C before you start the vector. So what we have now is a simple one-line program that says, I want a new object called die to be a vector of values from 1 to 6. We can go ahead and run just the one-line program, see if it's working, by highlighting the program and then coming over here to edit and doing run line or selection, so that we'll run the line or selection. So what it literally does is import that line or selection into the console and then runs it. And I can see by virtue of the fact that I got another cursor out that it did run successfully. It's not stuck in a loop of some sort or giving me any errors. But I don't really know for sure if it works, so sometimes what I'll do to make sure particular lines of a program have worked is to investigate whether the new object has been created over here. So I'll just type in die and make sure that the output is what I intended, and sure enough, the object die is now a vector of 6 values, 1 through 6. So it seems like it is indeed working. Okay, once we have a die created, what we like to do is roll it, and what that in R amounts to is sampling that vector where each one of these outcomes would be equally likely. So if we were to investigate sampling, we might want to know exactly how this sample command works. So there's a really nice feature in R that when you're in the R console, if you know a command's name and you want to know more about it, you can always type in $sample. If you precede whatever command it is with a question mark, what it does when you hit enter is it fires up your internet browser and takes you to the R helps space online. I guess the R documentation would be a more correct way to say that. And it takes you to the actual command description and usage and arguments and gives you the details of the command. And if you scroll down, then there also are a few examples of the way that the command is being used. So we could go here and read the description. It says that the sample command takes a sample of specified size from the elements of X using either with or without replacement. I'll get this a little bit bigger so we can read it. And the usages are one of two. There's a sample X size replace probability, or a sample.int n size replace false. So I think what we want to do is just sample. Let's go ahead and read about how the sample vector sample command works. The arguments are either X or n. So I'll read about X. X is a vector of one or more elements from which to choose. Okay, so that sounds right. So I think I want to use sample because I'm sampling from a predefined vector, our die vector. That means the next argument I should give it is size, which is a non-negative integer giving the number of items which to choose. And then replace. Replace says, well, should the sampling be with replacement? And then probability, and it turns out that anytime you see this as null, that means that it's an optional argument. But that's a vector of probability weights for obtaining elements of a vector being sampled. If I go down here and read a little bit more about prob, it will say that it's an optional argument, so we don't need to include it in our case unless we want there to be a different vector of probability weights. So what does that mean? Well, in layman's terms, it would mean that if we wanted to make this an unfair die, we could give 6 different weights, probability weights to the 6 sides, and make, for instance, the side numbered 5 more likely or less likely to appear than it would under equally likely sampling. So I'll go ahead and go back and check and see if I can use this particular command to create a role. So I'll go ahead and call out my my new object role, and I'll store to that object a sample of the die vector. Or I'm just going to roll it once right now, die vector 1 sample, and then the third command that I need to include was replace equals. So in this case, since I'm rolling a die, and I don't want to take away a face if I roll it again, I will let replace be true, because I certainly don't want to take away a face of the die when I roll it a second time, for example. Okay, well, now the question mark is this thing working? So I'll go ahead and select all. One way you can quickly select the whole program is by typing Control A. So I'll do Control A to select all, and then Control R to run. And it looks like it did run over here because I'm getting a cursor back. But it doesn't really tell me what my role value was. I could come over here and type it, for example, but one way you can get R to print out particular values or vectors is just to type them in the program itself. So Control A, Control R. Now I can see that the role that it sampled, so the number that it sampled from the vector die was 3. I'm going to go ahead and run it 2 or 3 times just to see how it's working. So it looks like it is working because I'm rolling a 3, a 6, a 6, a 4, a 1. Let's see if we can get a 2 to show up. It's going to take it a while for me to get a 2, but yeah, it looks like I'm getting all the values that could potentially could potentially result from the sampling of the vector die. So it looks like now I've mastered a single die roll. It might be kind of interesting to see, well, what if I sampled that single die 100 times? Are things really equally likely? So I'll go ahead and hit Control A, Control R, and sure enough, I have a stream of 1s, 2s, 3s, 4s, 5s, and 6s that were sampled when this particular die was rolled 100 times. The problem is now it'd be nice to know whether or not the 6s are occurring at roughly the same quantity as 5s, 4s, 3s, 2s, and 1s. So what we'd really like to know is not the roll itself, but a table of roll values. And you can do that by just simply typing table, parentheses roll. That will give you a table of results of the roll vector. And this is what we get in the output. And we can see that we get all of the 100 rolls here listed, but nicely tabulated here in table form. We can see that 1s, 2s, 3s, 4s, 5s, and 6s were the 6 outcomes, and then the second roll, or excuse me, the second line tells us how many occurrences of each outcome. And it does seem like they're roughly equivalent. Of course, we know due to probabilistic nature of rolling a die, these would always be exactly the same, but they're roughly the same. Might be nice to roll it a couple more times just to see. Ooh, we got a real different outcome there. 8 3s only, and a high of 24s. And a little bit more. Oh, there's 21 5s. It'd be interesting maybe to throw 1,000 at it and see what happens now. So we get an extremely large table of roll values, and now we see a little bit less variation, I guess, between the 6 outcomes. Maybe we should suppress the actual data here and take a look at what happens when I roll it 10,000 times. Then I can see that I'm getting something fairly close in terms of the number of 1, 2, 3, 4, 5s, and 6s that I roll when I roll this dice 10,000 times. So you can see that R allows you to quickly adjust certain parameters and commands and to inspect behaviors of certain probabilistic experiments fairly rapidly. Okay, so we've, I guess, accomplished that one sub-goal of rolling a single die. Now the question would be, how do we roll 2 die? And the nice part is we can just simply adjust our strategy, and instead of having a single die being sampled, what we'll do is we'll copy that line of text, put a plus here, and repeat it. So if we think about what this is going to do, it's going to be a sample of the die vector 10,000 times. So this will be a 1 by 10,000 vector of single die rolls, and I'll add to that a 1 by 10,000 vector of another single die rolls. And when vectors are added, of course, they're place-wise added. So the first place in this vector will be added to the first place in this vector, and so on. And so what we'll end up producing is a 1 by 10,000 vector that has as each of its entries the sum of 2 die rolls. And we'll go ahead and make this even more friendly for us to use by adding to the first line of text the number of iterations that we want to conduct in the experiment. So you see that now what we're going to do is roll each die 100 times at it. So here we go. And the table of rolls shows that it appears that these middle values, 6, 7, and 8, are more likely to occur than these lower and higher values, the values at the extremes, the 2 and the 12. And that's as expected if you've thought about this from an analytical perspective, but let's go ahead and see if we get something similar when we run it again. And indeed we do get something fairly similar. There's a little bit of variation on these tails we can see, but in the middle roughly it seems like the probability of those outcomes is higher than the probability of outcomes at the extremes. It'd be nice probably now to run it for 1,000 rolls. And we get something that looks pretty good there. Again, seems to be mimicking what's going on in the previous table. One thing that makes it hard to compare these, though, is the fact that the number of rolls or simulations in this particular run of the program is, of course, different than in this run, so we can't really compare counts. What it might be nice to do is to compare proportions. So you can convert a table of counts into a table of proportions by adding a command prop table, which stands for proportion table, to the table of rows. So we now have a vector that's being tabled and then being converted into a proportion table. So I'll run it again, and now we can see the proportion of rows that were 2 and 12 are fairly low, whereas the proportion of rows of 6, 7, 8 are substantially higher in the middle. And if we run it again, we can then compare tables and see how much variation there is from simulation to simulation. And you can indeed see quite a bit of simulation, for example, or variation. If you look at the outcome of 7, I can see that in this particular simulation, 7 was a little bit less likely than 7 in this particular simulation. So what that's indicating to me is I haven't actually run enough simulations to let that variability settle out a little more. So I'll go ahead and run it 10,000 times and see what happens. So now I can see quite a bit of difference between what's going on here for 7 and what's going on here for 7. Well, no, actually those are fairly close. Yeah, and here is a little bit different. Oh, the way to tell if this is actually settling out would be to run it again and see if we get something similar between the two 10,000 trial simulations in terms of proportions of each outcome. And it does appear like there is a bit of variability. So if we really wanted to put the computer to use, we might as well bump it up one more level. In fact, I'm going to go 2 more levels. So I'll go to 1,000,000 trials now. And it will take it a bit of time to think. Be careful not to add too many zeros at a time, because you can actually get into trouble in terms of memory usage in your computer. But at this point, I'm going to run it twice and compare the outputs of the two proportion tables just to see if we actually have somewhat of the same answer. It looks like to about the 3rd decimal place or the thousandth place we have pretty good agreement between the two simulations, which leads me to believe that we're very close now to accurately predicting the probability of this particular set of outcomes due to the fact that we don't have a lot of variability between simulations. I'll go ahead and run it one more time for a 3rd check and just confirm that, yeah, 1,000,000 trials, it looks like, or 1,000,000 trials in our simulation seems to be enough to where we're pretty stable in our relative frequencies for each of these outcomes. And so I would, at this point, use this particular table to check against an analytical solution for the 2-die roll to see if they actually are similar. One last thing I want to show you before we conclude is that you can also use R to get all kinds of beautiful visual displays of statistical results. And one of the things that might be nice to do here would be to do a histogram of roll and to get a sense of what these counts look like as a visual picture. And you can see that now what we have is, I'm going to go ahead and tile my windows vertically here again. We have a histogram off to the right here that's showing the frequency of outcomes that fall in these different bin widths. Now I'm a little bit worried about the bin widths because between 2 and 4 I can see there's at least 1, 2, 3, 4 bars. So it appears that it's chosen 1/2 as the bin widths here. So this would be 2 to 2.5. And that doesn't really mimic my data, which is in integer form. So I'd like to actually add an extra command to the histogram call that would actually adjust the bin width. So I'll act like I don't know how to do that and go into histogram's description in the R documentation, and I can see that there is indeed a argument that allows me to control the breaks. And if I come down to the argument's description, it says that breaks is one of a vector giving the breakpoints between histogram cells, or 4 other possibilities, but a vector will work just fine because we want breakpoints at integer locations, and we can easily write a vector for those integer breakpoints. So I'll come back and add a command here. So breaks will be a vector from 1 to 12. One way to do that quickly is just to do 1:12 instead of 1, 2, 3, and so on. We'll go ahead and run it again, and Now we can see the histogram of roll is a little bit nicer in its display of the frequency of outcomes, and we see quite a bit of symmetry, and indeed it seems like 7, the bar representing 7, is the most common outcome when 2 dice are rolled, and then the outcomes on either side of 7 fall off in a symmetric fashion, and 2 and 12 seem to be the least likely outcomes. Okay, well, that would be a quick introduction to how you can use R to write a simple program in 5 lines to run a fairly robust simulation of a probabilistic experiment.